Thanks very much. Yeah, I'm work at Media Math here. I work on the creatives team. I'm actually a manager here, and I have 2 opening slots for Scala devs. I'll just put that out there. We do the ad serving, so lots of requests a second, fun stuff, good challenges. All right, Autolifts, automatic type-derived lifting. Wow, this sounds pretty fancy and cool. This actually came about, or this whole library happened. That talk that I gave last year here, I actually went around the country, started giving that talk, and over in Boston, Eugene, the guy that writes SBT, he stopped me at one of the slides, and he was like, it's like, I really don't care about the rest of this, but that's cool. Can you put that in a library? And what he didn't know is that prior to the talk, assembling it up and getting the slides ready to go, I had actually experimented around with a lot of things like that one slide. So I took those ideas and I started putting it into this library. And as I started getting these things in, I got really excited because I thought it was onto something. And I think this is really cool, and it's finally at the point where I can share it and open it up and let you guys see. But before we begin, type-derived lifting. Well, lifting, what is it? You hear that and you're like, yeah, do you lift, bro? Yeah. But what lifting is it's a really simple concept that they've given this weird term to, like they always do in functional programming, which it really doesn't need to. If it was what it was, people would know it immediately. So let's say we have some function, like a really easy function. We're just squaring integers here. We're taking something that has a signature of int to int. And let's suppose we have an object. Look at this, a list of integers. This is great. This has a signature of listInt. And if we try and naively use these two together, we're going to get a compile time error, because Scala is going to say, like, this is a list of int. This function works on int of int. What are you doing? None of us actually would do this. We'd grab list and we'd say dot map square, because that's what you do. That's kind of what map is for. And so lifting, if you think about it, it's where we have a function and we sort of invert this and we say, like, okay, make my list the argument. So we take something, in essence, if you look at this and you sort of squint and take a step back, that has a signature of int to int, and we lift it into
Sorry.
Yeah.
There's something wrong with your mic.
There's something wrong with my mic.
You should probably move that thing. Sorry about that.
Go for it. How's that? Yes? I could put it in my pocket if it starts like...
Yeah, it just moves a lot.
It just moves a lot. All right. I'll try and keep... Sorry. So, all right, lifting. We have this function int to int, and we want to lift it into this higher kinded context. We want to lift it into lists. So now we actually come out with a function called, which has a signature of list of int to list of int by using this function that had int to int. And we can do this easily with a list because it has this map function. But this map function, if you think about it, lots of other things have map. Options have maps, sets have maps. And that's because these things are all something called a functor. They're actually more than just that. But we can generalize this concept and we can say, as long as in Scala there exists a functor for the type I'm trying to work on, I can lift it up taking this function. So I might write this lift function like I have up there, and I just call it like this, lift list square. And if you don't know what a functor is, it's again a very, very hand wavy. It's just something that has a map. I mean, that's it. And if you've never seen functor, if you've never like seen Scala Z or cats or one of those various types, that fn map f, if we had list up there in f, it's actually just underneath the hood delegating to map.
Is that blue list different?
Is that what? Blue list different? Nah, that's because my highlighting is not the best. So yeah, I should have probably fixed that. All right, so that's really cool. It's a nice, neat little abstraction. So why do we want to lift? I mean, why not just use map? I mean, it's simple, it's there, it's basic, it's fairly straightforward. Even works when we have like weird nested types. I mean, that's readable, right? You can see what's going on. It's nice, got nice indenting and things like that. But as your types start getting more complicated, as you start stacking them up, you're going to start having to use a lot more maps. And if you don't include one of these maps, generally you're okay, because the compiler will come back and say like, no, you missed one, you goofed, or you went a little too far. But it does start getting gnarly. I mean, I've put this all into one line so we could be like, oh, easy, 1, 2, 3. But most of you guys would start indenting it. It would look kind of like a set of staircases or sideways pyramid or something like that. We'd start having the same issues or same complaints that you often see when people write jQuery code. It keeps sort of moving off to the side, and you kind of have to slide your screen over to see what's going on. So that's not very cool. And then you deal with something like this, and I give up. How many of you guys have actually write code like that with a type that's so deeply just one person? Okay, a couple more. So we got a bunch more people. Awesome, cool. For those that don't, why not? Is this just? It's scary, right? This is like a real pain in the ass to deal with, right? But look at what this says. I mean, let's take a second and actually see what this would say just looking at the types if this were an API call. So the first thing is a future. This is saying, okay, this is an asynchronous call. I'm going to get this at some point. Great, API should be asynchronous. Awesome, good deal. We have an option that says like something may not be there. So maybe you're looking at accounts / the ID / purchases. And you've got some sort of form field that goes in. So option would tell you, does that account exist or not? Validation, if you've never seen it, it's kind of like try, only you can accumulate the errors. So if you have like 3 fields in your form that are invalid, you can actually hand back to the user going, these 3 forms are wrong, rather than the user changing one form and getting a thing back going like, no, you messed this one too. Like that's just user friendly. And then this is the thing that we want. If I didn't do this, if I tried to avoid this stuff and avoid like the compiler coming back and like making me explicitly check and handle each of these cases, I might just do a future of list. But now, list of, a nil, that can be both that the account doesn't exist or that there are no like purchase records or something like that. And if I had an incorrect form, I might stick it as exceptions in the future. And then far away from the call site, I have to remember and I have to keep in my head this mental track of the different errors and exceptions and then try and handle them from memory essentially. Or write some unit tests to have it. All these things that the compiler itself could do for us. But this is a real pain to deal with. I mean, let's not kid ourselves. Here we go. So this is what it might look like with lifting. And we're being a lot more explicit what's happening here. I mean, we're actually forming this ladder that we can walk up and climb here. We have list and validation and option and future. These things are composing together. And now we have a function that isn't just int to int. It's future option validation list int to future option validation list int. And then, oh, really? Yeah, really. It's just like that. It's simple. It's basic and clear. But I just want to sort of, let's play a mental game here, or let's do a thought argument, if you will. So push button solutions. Everybody likes push button solutions. So You're on the 46th floor of the building, right? This is where you came. This is where we are. How'd you get here? You took the elevator, right? So when we think about things that we have or things that we interact with in the world, which would we rather do or which would we rather have? Do we want to have things that are easy to use or things that were easy for some other person to make? And I think the answer is easy to use. And I'm going to go a step further and try and prove it. Stairs. Stairs are really easy. From an engineering perspective. I mean, they've existed from the dawn of time. Probably like, there's this wall that's really high. If I build it any higher, I won't be able to see what's going on. I should probably fix something. So we make stairs. We take a board and we place it here, and we place the next board up and a little bit further, and it's easy to use. It's self-explanatory. You just walk up it. But it's a very manual process, and manual sucks. Elevators, on the other hand, they're easy, right? Except if you're going to make them, think about it this. You're going to take a metal box and you're going to take it from ground floor and you're going to move it up like 500 feet. And it's got to go up and down. So you have to put an engine in there and some sort of pulley system. And you have to have emergency brakes in case the pulley system fails. Or you actually, the biggest challenge, I think, is electricity. I mean, no one's going to get in a box that's dark and go up 500 feet, right? No one would trust that. So getting electricity into a box that can go, I mean, this building is actually 72 floors, so up and down 700 feet. That's actually pretty, I'd like to know how they do it, because I don't really know. So when you got in and you walked through the gates and got through security, did you go up to the elevators and go like, wow, those things are really complex. I'm taking the stairs. No.
There was a guy that pressed the button.
Yeah, you pushed the button, you walked in, no, someone did it for you. Wow, that's even better. You didn't even have to push anything. Well, it's got a really nice interface, but so you ignored all this complexity and that sort of thing. And if you're building something, I mean, think about the converse. Who's going to build a 72-story building with just stairs? I mean, who's going to rent the 72nd floor? Nobody. So when we look at these things and we talk about this stuff, what I just showed, lifting's cool, it's concise, it's nice, it's really beautiful, but we still have to do it ourselves. I'd actually have to write that in my code. And that's kind of the problem that Autolifts is going to solve. I'm going to do that for you. So I'm going to have this nasty future option validation list int, this crazy thing, and I'm just going to do .lift map square. And if you've never seen Scala test, the when ready strips away the future, and out I get exactly what I've done. And maybe I had an option success list of 1, 2, 3. Now I've got out my sum success list 1, 4, 9. And it just works. I get the right values, I get the right types. But more than just that, more than just forcing us down like into just using the ints, this thing's going to be type driven. Much like the buttons on the elevator that you press to say which floor, you give the signature of the function to the compiler and it says, I need to lift it this far up. So it does that for you. So now future list option int, I pass in an option int, and now I'm going to get out a future list int. And it'll just work. Or maybe I passed in a none, I got out a 0. Flat map. Because if you got map, why not flat map too? So this works. As a matter of fact, a whole bunch of functions I put in. There should be a lift map there. A whole bunch of functions that come in, and I'm just using an implicit class, and it works off of just a higher kind of class, and it provides you, a lot of things that you would see: flat map, fold left, fold right, filter. And if you haven't seen some of the other ones, don't worry about it. But I've been slightly coy because I didn't list the return type there, and here's where the real magic happens. So lift map is actually defined such that if I know what my object is, my f of a, this higher kind of type, I pass in this function b to c, and then I will get an implicit, and that implicit will be specific to the object and my function. And that weird lift.out, that's a dependent type. So that is a type parameter that is explicit and defined to the type parameters in that liftf, but it's not in any. So that's why I can do like, lifting the option of int, a function of that, or a function of int, and I still get out the same type. That is a compile time property. At compile time, it will come out. The compiler will do it. And it's built off of, behind the scenes, some type level induction. And I'm just using that dependent type to pass out the result of what it should be. So that's what it looks like under the hood. So let me flip over and try and you guys can interrupt me at any point in time, but let me show you a little bit what this sort of looks like. Can I make it bigger? Yeah.
Plus.
What's that?
Command plus.
Yeah, all right, here we go. Awesome. I'm going to go over here and just seal some stuff here. That's not what I wanted. Awesome. So I just imported a whole bunch of things. So I've imported my Autolift, and then I've imported a whole bunch of Scala Z underneath the hood. Notice, however, everything that I showed you up to this point in that library, those implicits, you saw no Scala Z. So if you guys don't know what it is or don't want to use it, you actually won't see it in any of your return types. It's hidden in underneath the hood. That was another goal of this library. So let me just copy this. So now I've got this function that returns a list option int, and I can take any of these. So the first guy here that we're going to, well, that's pretty shitty. Let's do this. Let's do something else instead. All right, olist dot lift map. The first thing I want to say is that any is not a type of that or this list, but I'm still going to be able to work with this. I'm still going to honor the fact that functions are contravariant in their argument. Covariant, contravariant in their argument. So they can accept anything. And we could take this, and I can use it in a bunch of different cases here. Let me do this. And I can actually have this function. Well, I'll come up with a quick. Awesome, cool. I'm not going to get fancy here. So if I've got some list of bar of 1, it will work just fine. What's that? 2 parameters. What did I? So it'll just work that way too. It's great. You can. It's the same thing as, in this case, map, or as I nesting rows. It will continue to follow suit and keep pace with you, preserving like the same kind of things that we would expect out of any sort of function whatsoever. So that's cool, and that's really great at the object-oriented style. Like we have list, and then we put methods on it, or like any sort of object that we have that then has a method, because we can get some nice clean syntax, and it looks good, and that's all wonderful. But Scala also has this sort of like dual quality where it's trying to be both OO and FP. It's trying to be like 2 sides of the coin, and so anytime you have these 2 sides of the coin, you get ideas from both sort of coming in, and so what I showed before was this syntactic extension to add these methods onto objects. Instead, I'd actually like to then show the other half of the library, which is a bunch of lifting contexts. And to explain what these are a little bit better, let me talk about a different language completely. If we're going to talk functional programming, we're going to talk Haskell. Actually, we could talk Lisp, but let's talk Haskell. So liftm. This actually exists in Haskell. If you've never written Haskell or you can't read this, does anybody know not what's going on here? This is just, again, a higher order function. It takes in some function of a to b, and it returns, again, it lifted up into a monad, but for any sort of monad. And this is slightly different than what I had before, which, I was using just functors, even though technically it's really not doing anything more advanced. So this liftm composes. And composition in Haskell, that's a dot. That's the composition there. So if I have a function of a to b, that's f, and g is b to c, and I lift m this up, I now have an m of a to mb composed with an m b to mc. That's ma to mc. Well, that's equivalent to the other side. And it also composes with itself. So I can do nested compositions of this stuff and manually come up with a bunch of liftings, manually. That's actually kind of hard to do in Scala, though, because we actually have to be explicit about the type of the monad, because monads are a type class in Haskell, and it's sort of built into the language. In Scala, we're sort of bodging it on using the type class pattern. We don't have real type classes. So liftm's cool, but there's a whole family of these guys. There's all the way up to liftm 5, so you can do things of more arity than just this. liftm2 works on functions of arity 2, and it's here where the fact that we're using a monad sort of comes out, and we start doing things. So one of the things about lifting is, or when you do it, is when you lift it up into this other context, you add a function, you return a function. So you never lost the intrinsic properties of the thing that you were lifting. It always retained the fact that this was a function and now it's a function again. But you can also gain some things too. So in this case, we're mixing in, we're lifting it into a monad. And so we can use the properties of a monad to do some really nifty stuff. So this liftm2, this addition with these two lists, 0, 1 and 1, 2, is equivalent to the function right below. And if I were to run this out and I look at the command line, I'd actually get out 1, 2, 2, 3, a single list of 1, 2, 2, 3. Again, using the fact that monads compose with themselves only to get out just a single list, the same way I do here. But again, as cool as that is, any of this stuff that I want to do with nested types, I'd have to manually do it. So Autolifts, the same sort of deal as we did with the object-oriented approach. I have a bunch of functions like this, some lifting context, where I can pass in this function, this arity2, and it will work the same way as it did before. As a matter of fact, I can even start passing in nested types, and it will work the same way with monadic composition to come out with the result that I would expect. So here's list option 0, none, composed with list option 3. Well, the only thing I'm going to get out, because none flat map something else is always none, is going to be this list option 4. And like before, I provide a whole bunch of these contexts. So one for map, flat map, filter, lift a, that's with applicatives. If you don't know what those are, never seen them, don't worry about them. But they're there if you need them. But here I'm using the object-oriented properties of Scala because getting these type classes sort of work out is difficult, and then trying to get the end and the compose and that kind of stuff, it should still appear, or at least work in the same manner of a function that I had before. So I put these things in an object, and I added a map too, because this actually it's essentially a functor. And then the way it works is actually that apply method. And if you look at it a little bit, you squint it a bit, in this case, I know what my function is. It's A to B. In this case, the lifting is, these guys are working on the function. And now they can work on any type of object they're given them, or as opposed to the other way, the syntax extensions have an object and they can work on any type of function that might compile. And they're both built upon this same inductive proof, the same like lift-f that's coming in, only the arguments are different or slightly different. So there are some limitations, and I do have some future plans for this library to try and address some of these limitations. The first one, though, is partial functions. This is like a chicken and an egg problem, and I don't know how to solve this, so I don't think I can. Generally, with your map, you know what the type's going to be. It's quite explicit. It's A to B. In this case, even though you and I can look at this and say like, well, that's got to be a partial function on list of any, the compiler can't figure that out. It's got no context because the implicit parameter that I'm going to build depends upon the type of the function, but a partial function depends upon that type information and chicken and egg. I don't know which one's coming in which, so I get this weird compile error. Second thing is for comprehensions. That works because that's flat map and map under the hood. There's built-in syntax into Scala, the language. It won't work for these. I do want to address that, though. I'm going to try and do a little macro magic to transform these for comps into sort of the lift M's underneath the hood and sort of come out that way so that we can have the same sort of logic. By the way, if you don't want to use this library, if you're looking for something to think about in a comparison, there are some things called monad transformers. They will work with the for comprehensions, but I'm telling you that my library is faster. And yeah. I only went up to 3. So Haskell went up to 5. Scala is supposed to go up to 22. I wrote the third one of each, and then I said, dear Lord, I need to write something to write this for me, and I just haven't gotten around to it. But I will eventually do that. This library is based on Scala Z. So if you guys are using cats in your code base and you want to move to that, and I'm putting in something that's slightly conflicting, don't worry, I am going to fix this. Miles Sabin actually came out with a wonderful tool, and that's going to allow me to build out sort of a swappable back end so that if you want to use cats, or actually, Prasad, you asked for Algebird. I don't know if you're still here, but I'm going to do that one first because it came from in-house. But then cats, and that way you can pick and choose which one you want to bring in and which one you want to import. So these are all the plugins that I'm using for documentation. Because documentation sucks and it's hard. And I will tell you this. I've got all these markdown things using SBT Tut, which Rob Norris did. If you guys have never used SBT Tut, you write markdown, and it actually compiles all your code examples so that you have to keep honest with this stuff. So this will keep pace with the library, and if it doesn't, there's compile error, and you know. I just am having the damnedest time getting this into Jekyll because Jekyll and me is like, for some reason, a foreign language. So if there's any of you that know Jekyll and want to help me, I would really appreciate this. Or if like you want to get into some open source stuff, this is it. That's your ticket right in, right there. And I'd be eternally grateful. I'm at 0.3. So that should tell you that this is a library that's still a little experimental. You can take it, you can use it. I would love for you to do it. I can guarantee you it will compile because everything is done at compile time, and if it doesn't, you can open up a ticket, but I doubt you'd have problems. Do know, though, if you're writing your own types and that sort of thing, that because it's based on Scala Z and it's using Scala Z under the hood, there are certain guidelines for some of this stuff. So lift map, I need functors. Lift flat map, I need functors all the way down to actually a bind. So I don't need a full monad, I just need a bind. and things along those lines. So bind is just something with a flat map, sort of. I'm wishy-washy. There's like deep theoretical mathematical stuff. The code's over at my GitHub if you guys want to take a look. And that's it.